Learning outcomes. After studying this module, you will be able to understand the concept of Pareto efficiency, know the two fundamental theorems of welfare economics, identify social welfare function, and evaluate welfare maximization. Introduction. Welfare. Welfare economics is the branch of economics which deals with normative issues. It deals with the way various economic arrangements affect the welfare or well-being of each and every member of the society. A major concept in welfare economics is the notion of Pareto efficiency in evaluating economic allocations. But it must also be remembered that Pareto efficiency has nothing to say about the distribution of welfare across people. Consumer utility, production mixes, and factor input combinations consistent with efficiency comes up with lots of combinations. In other words, there will usually be many Pareto efficient allocations. So, how can a society choose the most desirable among them? This decision is made when we specify the social welfare function which embodies value judgments about interpersonal utility. Since the concept of efficiency plays a major role in welfare economics, we begin by discussing it in brief. After that, we will study the two fundamental theorems of welfare economics. Next, we will study the idea of social welfare function and its implications. Pareto efficiency. A Pareto efficient allocation is one where we cannot make an individual better off without making the other one worse off. To reach the ideal state, three criteria are required to be met. 1. The marginal rates of substitution in consumption are homogeneous, that is, identical for all consumers. This happens when no consumer can be made better off without making others worse off. Or we can say when MRS 12A is equal to MRS 12B, where MRS 12 is the marginal rate of substitution between good 1 and 2 for consumers A and B. The second criteria is the marginal rate of transformation in production is also homogeneous for all products. It happens when it is not possible to increase the production of any good without reducing the production of other goods. Or we can say when MRT LK1 is equal to MRT LK2, where MRT LK is the marginal rate of transformation between labor and capital. Third criteria is the marginal rates of substitution in consumption are equal to the marginal rate of transformation in production, which means that production processes and consumer wants must match with each other. That is, MRS 12I is equal to MRT 12, where MRS 12I is the marginal rate of substitution between good 1 and 2 for consumer I. Fundamental theorems of welfare economics. There are two fundamental theorems of welfare economics. The first welfare theorem and the second welfare theorem. The first welfare theorem. This theorem states that the equilibrium in a set of competitive market is Pareto efficient. This is illustrated in figure 4.1. It turns out that the market equilibrium allocation is Pareto efficient. This can be proved as follows. An allocation in the Edgeworth box is Pareto efficient if the set of bundles that A prefers does not intersect the set of bundles that B prefers. That is to say that the indifference curves of the two agents A and B must be tangential to each other at any Pareto efficient allocation in the interior of box. If the two indifference curves are not tangent at an allocation, then they must cross. In such a situation, there must be some mutually advantageous trade. So that point cannot be Pareto efficient. But at the market equilibrium, the total amount that A and B want to buy of each good must equal to the total amount available. Said another way, the set of bundles preferred by A must lie above his budget set, and the set of bundles preferred by B must lie above his respective budget set. This implies that in equilibrium, each person is choosing the most preferred bundle in his budget set, and the choices exhaust the available supply. Thus, the two sets of preferred allocations cannot intersect. This means that there are no allocations that both agents prefer to the equilibrium allocation. So, the equilibrium is Pareto efficient. This can also be shown algebraically. Suppose that there is a market equilibrium that is not Pareto efficient. Then it can be shown that this assumption leads to a logical contradiction. To say that the market equilibrium is not Pareto efficient means that there is some feasible allocation y1a, y2a, y1b, y2b such that y1a plus y1b is equal to omega 1a plus omega 1b, and y2a plus y2b is equal to omega 2a plus omega 2b, where omega 1i, omega 2i are the initial endowments of good 1 and 2 for agent I, and y1a, y2a is preferred to x1a and x2a for individual A, and y1b, y2b is preferred to x1b, x2b by individual B. The first two equations say that the y allocation is feasible, and the next two equations say that it is preferred by each agent to the x allocation. But by hypothesis, there is a market equilibrium where each agent is purchasing the best bundle he can afford. If y1a, y2a is better than the bundle that A is choosing, then it must cost more than A can afford, and similarly for B. That is, P1 y1a plus P2 y2a is greater than P1 omega 1a plus P2 omega 2a, and P1 y1b plus P2 y2b is greater than P1 omega 1b plus P2 omega 2b. Now adding these two equations together, we get P1 y1a plus y1b plus P2 into y2a plus y2b is greater than P1 into omega 1a plus omega 1b plus P2 into omega 2a plus omega 2b. Substitute from equations 4.1 and 4.2 to get P1 into omega 1a plus omega 1b plus P2 into omega 2a plus omega 2b is greater than P1 into omega 1a plus omega 1b plus P2 into omega 2a plus omega 2b. This is clearly a contradiction since the left hand side and the right hand side are the same. We derive this contradiction by assuming that the market equilibrium was not Pareto efficient. Therefore, this assumption must be wrong. It follows that all market equilibria are Pareto efficient, that is the first theorem of welfare economics. The first welfare theorem guarantees that a competitive market will exhaust all of the gains from trade. An equilibrium allocation achieved by a set of competitive markets will necessarily be Pareto efficient. The second welfare theorem. This theorem states that when preferences are convex, a Pareto efficient allocation is equilibrium for some set of prices. This is illustrated in figure 4.2. Consider that at a Pareto efficient allocation, the set of allocations A prefers is disjoint from the set that B prefers. This implies that the two indifference curves are tangent at the Pareto efficient allocation, that is point X. Let us draw a straight line that is their common tangent. Suppose that the straight line represents the agent's budget sets. Then if each agent chooses the best bundle on his budget set, the resulting equilibrium will be the original Pareto efficient allocation. Thus, the fact that the original allocation is efficient automatically determines the equilibrium prices. The endowments can be any bundles that give rise to the appropriate budget set, that is, bundles that lie somewhere on the constructed budget line. Now consider figure 4.3. Here the illustrated point X is Pareto efficient, but there are no prices at which A and B will want to consume at point X. The optimal demands of agent A and B do not coincide for the given budget. Agent A wants to demand the bundle Y, but agent B wants the bundle X. Demand does not equal supply at these prices. The difference between figure 4.2 and figure 4.3 is that the preferences in figure 4.2 are convex while the ones in figure 4.3 are not. If the preferences of both agents are convex, then the common tangent will not intersect either indifference curve more than once and everything will work out fine. This observation gives us the second theorem of welfare economics. If all agents have convex preferences, then there will always be a set of prices such that each Pareto efficient allocation is a market equilibrium for an appropriate assignment of endowments. At a Pareto efficient allocation, the bundles preferred by agent A and by agent B must be disjoint. Thus, if both agents have convex preferences, we can draw a straight line between the two sets of preferred bundles that separates one from the other. The slope of this line gives us the relative prices, and any endowment that puts the two agents on this line will lead to the final market equilibrium being the original Pareto efficient allocation. Social welfare function. Up until now, we focused on considerations of Pareto efficiency in evaluating economic allocations. There are other important considerations also. Pareto efficiency is in itself a desirable goal, but there will usually be many Pareto efficient allocations. How can society choose among them? This decision can be made by specifying the social welfare function. A social welfare function provides a way to rank different distributions of utility among consumers. Now the question arises as to how one might go about adding together the individual consumers' preferences to construct some kind of social preferences. Before we examine this question, it will be worth examining whether such an attempt is logically warranted or not. Arrow's Impossibility Theorem. Arrow's Impossibility Theorem shows that there is no perfect way to aggregate individual preferences to make one social preference. It is pointed out by Arrow that a social decision mechanism, way of aggregating preferences, should have the following features. A. Given any set of complete, reflexive and transitive individual preferences, the social decision mechanism should result in social preferences that satisfy the same properties. B. If everybody prefers alternative X to alternative Y, then the social preferences should rank X ahead of Y. C. The preferences between X and Y should depend only on how people rank X versus Y and not on how they rank other alternatives. Arrow's theorem says that the three very plausible and desirable features of a social decision mechanism are inconsistent with democracy. There is no perfect way to make social decisions. In order to find a way to aggregate individual preferences to form social preferences, we will have to give up one of the properties of the social decision mechanism described in Arrow's theorem. The most probable feature of social welfare function described above that can be dropped is the property 3. Actually, if the property that social preference between two alternatives only depends on the ranking of those two alternatives, then certain kinds of rank order voting become possible. Different types of welfare functions. Given the preferences of each individual I over the allocations, we can construct utility functions UIX that summarize the individual's value judgments. Person I prefers X to Y if and only if UIX is greater than UIY. Let us pick some utility representation. Then one way of getting social preference from individual's preference is to add up the individual utilities and use the resulting number as a kind of social utility. That is, we will say that allocation X is socially preferred to allocation Y if sigma UIX I1 to n is greater than sigma UIY I1 to n, where n is the number of individuals in the society. This works, but of course it is totally arbitrary, since our choice of utility representation is totally arbitrary. The choice of using the sum is also arbitrary. Why not use a weighted sum of utilities? Why not use the product of utilities or the sum of square of utilities? One reasonable restriction that we might place on the aggregate function is that it be increasing in each individual's utility. That way, we are assured that if everybody prefers X to Y, then the social preferences will prefer X to Y. This kind of aggregating function is called a social welfare function. A social welfare function is just some function of the individual utility functions W, UIX to UNX. It gives a way to rank different allocations that depends only on the individual preferences, and it is an increasing function of each individual's utility. Let us look at some examples. One special case mentioned above is the sum of the individual utility functions. That is, WU1 to UN is equal to sigma UI I equal to 1 to n. This is sometimes referred to as a classical utilitarian or Benthamite welfare function. A slight generalization of this form is the weighted sum of utilities welfare function, given by WU1 to UN is equal to sigma AIUI I equal to 1 to n. Here the weights A1 to AN are supposed to be the numbers indicating how important each agent's utility is to the overall social welfare. It is natural to take each AI as being positive. Another interesting welfare function is the minimax or Rawlsian social welfare function, which is given by W U1 to UN equal to min U1 to UN. This welfare function says that the social welfare of an allocation depends only on the welfare of the worst off agent, the person with the minimal utility. Another special form of welfare function is the individualistic welfare function or a Bergson-Samuelson welfare function. If Xi denotes an individual i's consumption bundle and UIXi is the individual i's utility level using some fixed representation of utility, then such a social welfare function will have the following form, that is W is equal to W U1x1 to U1xn. The welfare function is directly a function of the individual's utility levels, but it is indirectly a function of the individual agent's consumption bundles. Welfare maximization. Once we have a welfare function, the problem of social welfare maximization can be examined. Let xji denote how much individual I has of good j, and suppose that there are n consumers and k goods. Then the allocation x consists of the list of how much each of the agents has of each of the goods. If we have a total amount x1 to xk of goods 1 to k to distribute among the consumers, then the social welfare maximization problem can be stated as max w u1x to u1x such that sigma xi1 is equal to x1 to sigma xik equal to x to the power k. The feasible allocation that maximizes social welfare should have the following property, that is, a maximal welfare allocation must be a Pareto efficient allocation. The proof is easy. Suppose that it were not, then there would be some other feasible allocation that gave everyone at least as large a utility and someone strictly greater utility. But the social welfare function is an increasing function of each agent's utility. Thus, this new allocation would have to have higher welfare, which contradicts the assumption that we originally had a social welfare maximum. This situation is illustrated in figure 6.1, where the set U indicates the set of possible utilities in the case of two individuals. This set is known as the utility possibility set. The boundary of this set, the utility possibility frontier, is the set of utility levels associated with Pareto efficient allocations. If an allocation is on the boundary of the utility possibility set, then there are no other feasible allocations that yield higher utilities for both agents. The indifference curves in this diagram are called iso-welfare curves, since they depict those distributions of utility that have constant welfare. As usual, the optimal point is characterized by a tangency condition. The notable thing about this maximal social welfare point is that it is Pareto efficient. It must occur on the boundary of the utility possibility set. The next observation we can make from this diagram is that any Pareto efficient allocation must be a social welfare maximum for some social welfare function. An example is given in figure 6.2. Social welfare maximization. In figure 6.2, we have taken a Pareto efficient allocation and found a set of iso-welfare curves for which it yields maximal welfare. Moreover, as illustrated in figure 6.2, if the set of possible utility distributions is a convex set, then every point on its frontier is a social welfare maximum for a weighted sum of utilities welfare function. The welfare function thus provides a way to single out Pareto efficient allocations. Every social welfare maximum is a Pareto efficient allocation, and every Pareto efficient allocation is a social welfare maximum. Summary. Let us now summarize what we discussed in this present module. 1. A Pareto efficient allocation is one in which there is no feasible reallocation of the goods that would make all consumers at least as well off and at least one consumer strictly better off. 2. The first theorem of welfare economics states that a competitive equilibrium is Pareto efficient. 3. The second theorem of welfare economics states that as long as preferences are convex, then every Pareto efficient allocation can be supported as a competitive equilibrium. 4th, Arrow's impossibility theorem shows that there is no ideal way to aggregate individual preferences into social preferences. 5. Nevertheless, economists often use social welfare functions of one sort or another to represent distributional judgments about allocations. And 6. As long as the social welfare function is increasing in each individual's utility, a welfare maximum will be Pareto efficient. Furthermore, every Pareto efficient allocation can be thought of as maximizing some social welfare function.